Hey there, it's Shannon Math Chick Myers making another movie for your viewing pleasure. Today we're going to talk about confidence interval estimates for proportions when we're dealing with just one sample. So a point estimate, okay, is a sample statistic used to estimate a population parameter. The sample proportion p hat is the best point estimate for the actual population proportion, which we won't know most of the times in life. Now we'll just call it P here. Actually, you might see it notated as pi sometimes, but since most people aren't used to seeing it that way, we'll use P. The A confidence interval, which is shortened CI, is basically a range of values. So this point estimate that we have, there's always a little error when you're estimating. So this range of values will cover the true value of the population parameter with some specified probability. So remember in the lecture we had before, the confidence level is not the probability that your parameter is in the interval. It's the probability that your interval covers the parameter. And I know that seems like a kind of a picky distinction, but just tuck it in your brain and take it out when you want to be a math nerd like me. All right, the confidence level is chosen by the researcher. If you want to be very, very certain that confidence interval you construct contains the population parameter, you choose a greater level of confidence. Keep in mind that the higher the confidence level, because you want to play it safe, right? The wider the confidence interval. So you want to find a balance between, certainty and not having just this huge amount of possible values that could be in the interval that covers your parameter. All right, so let's check it out. Here, a very typical level of confidence is often a 95% level of confidence. Now, remember that for this one, we need to think about, okay, 95% level of confidence. Well, we need to find the corresponding z-score that's going to have an equal amount of area in the tails. So 100% minus 95% is equal to 5%. Do you agree? So if I divide that 5% by 2, I'm going to get 2.5%. With me so far? So I want to look for the corresponding z-score, wherever it is, which will give me an area of 0.025 in each of these tails, okay, in our standard normal. So if I go to our calculator and actually let's figure out what that is, okay? So here one way a person, could look at this is if I found the z-score, because remember the table does a less than, so if I found the z-score that corresponds, so I want so z star is how we usually word this, is the z-score, which corresponds, in this case, to good, a 1 minus 0.025 area, which of course is equal to 0.975, and so that of course would be all of this from here to here, right? And I know that's a little bit too much area, but that's okay, because remember that the standard normal is symmetric. So if you find this z-score, you'll just put the opposite sign on the other one and you'll have both boundaries. So let's check it out. All right, so here I'm going to go to second distribution, and what do we want to do? We want to do inverse normal, right? And we need to put the area, and I believe that was 0.975, and then I think that's all we need to put because it's standardized. So the z-score corresponding to that is 1.96. I'll go ahead and I'll take a screenshot of this. All right, so that's how I got this z-score of, so here what we really did, if you want to think about it, is we said the probability that z1 is less than z is equal to, well, we knew that answer, right, from our work up there. And so we found that z1 is approximately, with the calculator, we did z1 was approximately 1.96. Okay, so far? So these z-scores here are positive 1.96 and then negative 1.96. So that would be our z star in this case, all right? And negative z stars, the negative 1.96. Groovy? Now, just to check it out, let's look at what would a 99% level of confidence be like, or look like as far as this grid. Well, you want to be very, very sure, don't you? So it's going to be way out here somewhere. And so here, again, 100% minus, so now we're working on a 99% confidence level. And so 100% minus 99% is equal to 1%. And if I divide that by 2, right, I will get 0.5%, right? Write that out. And then what's going to happen? This in decimal form is going to be 0.005. Okay, so 100% is 1 minus 0.005, and that's equal to 0.995. So again, we go back to our calculator and we go second distribution, inverse normal, and we have, what did we say that was? 0.995. And we get 2.575. So the probability that z1 is less than z equals 0.995 gives us Z1 is approximately 2.5. So here, this is going to be further along. And so what we got was, this is about 2.58. And over here, this is about negative 2.58. And so again, our whole region is going to be all of this area now that we've, you know, adapted for the two tails. Okay? All right, so in this case, our Z star was equal to 2.58. Groovy? All right, so now if we go on and we work a problem, all right, let's just talk very quickly about a critical value. So I just gave you two examples of critical values, but we use them in both confidence interval construction and hypothesis testing. A critical value is used in both confidence interval construction and hypothesis testing. So for confidence intervals, plus or minus this value divides the horizontal axis into three intervals. So if you look here, we had the orange this one here, right, is one interval, but this would be like minus infinity to negative 2.58. Over here would be positive 2.58 to infinity, and inside this would be negative 2.58 to positive 2.58. All right, that's what I mean by the three intervals. So the two tails represent the standardized values which are not contained in the confidence interval. They're not considered likely values. And the middle interval of standardized values consists of the confidence interval used to estimate the population parameter. Now again, there's going to be some shift because we're going to be using p hat, so it won't all be standardized, but this gives you sort of an idea of what happens if you were just on the z-scale. All right, the next part of the puzzle is to find the standard error. Since we do not know the population proportion, typically, which is denoted P, remember, we use the point estimate P hat and its complement Q hat, which equals to 1 minus P hat, because remember it's approximated, it's the binomial being approximated. And P hat, I don't know if you remember this, is equal to the number of successes over the sample size n. So we have the standard error of the point estimate, p hat, is equal to the square root of p hat times q hat over n. And the confidence interval is constructed by adding and subtracting from, adding to and subtracting from p hat the critical value times, the standard error. Groovy? All right, so in statistics ease, for the whole interval, we would have, so remember, if we do it as an inequality, we are estimating p. We don't know it. But what we know is that it'll be between, on the right side, our point estimate p hat plus the z star business, right, times the square root of p hat q hat over n, which is the point estimate's standard error. And on this side, we would be subtracting that. Groovy? All right, so here we go. if we just did it as an interval, which I don't know if I'd recommend for you right now, because we are going to be constructing confidence interval estimates for means as well. So anyway, I kind of like the first way better, but this is perfectly fine as well. In interval notation, you do not specify your variable. It's known by the context of your problem. All right. So in the first example, here we go. We've got a simple random sample of 80 MiraCosta College students. 18 of the students surveyed indicated that they vaped. Please construct and interpret the 95% confidence interval estimate of the proportion of MiraCosta College students who vape. All right, well, there's a few things going on. What do we need to find? Doesn't have to be in order, but we might want to find our point estimate, right? And its standard error. A lot of times they just call that SE. All right, so with this, we have, remember that P hat is equal to the number of successes over the total number in the sample. So, what do you think? What is X? Beautiful. X is the 18 who vape out of the 80 sampled. So, good so far? All right, so let's go ahead and get the proportion that, or the decimal that goes with that. So that would end up being approximately, so what did I have? 18 divided by 80, enter, and math, decimal, enter, 0.225. Actually, it's not an estimate, it's an exact. All right, so that's equal to 0.225. Cool so far? All right, so this is our point estimate. Its standard error, remember, is the square root of P hat Q hat over N, which will be the square root of P hat times 1 minus P hat using complement over N. And let's see what we get. So P hat, remember, was 0.225. All right, that makes a 1 minus 0.225 equal to 0.775, I think. And then our sample size was, beautiful, 80. And this one I'm pretty sure will be approximate. So let's see what we get. So I'm going to put parentheses. Actually, you know what? It'll be, so let's do square root of 0.225 times 0.775 divided by 80. I think we're going to be good. Perfect. We get 0.0467. I'll go to the fourth place. 0.0467. All right. Well, we're getting there. What do we need to find now? Well, how about Z star, right? We need to find Z star to complete the interval. so in this case, we're looking at a 95% confidence interval estimate. So remember, when we were looking over at the other deal, you know, you have your little standard, you have your standard normal, something like that, right? And here we want to look for this region to be what? Beautiful, half of 5%, right? Because we want the big body of it to be 95%. So 5% divided by 2, remember, was 2.5%. And in a decimal, what was that? 0.025. Good so far? So again, finding the probability that some z1 less than z is equal to, what is 1 minus 0.025? Awesome. It is 0.975. And remember, we found it last time, but we'll do it again. So if we go to second distribution, the inverse normal, and if we hit, what did we say, 0.975, we get, awesome, 1.96. All right, so Z1 is equal to 1.96. And so that means our boundary values here, this one would be negative 1.96, and this one over here would be positive 1.96. And they just are on the scale here, and the corresponding regions to the in the tails is 0.025, and the middle region is your 95%, right? So this whole area right here contains 95%. Awesome. All right, so what's the next step? Construct our interval. Alrighty, so when we construct the interval, the general formula, remember, we want to find an estimate for p, right? We're going to use p hat to find it, and on the left we got to subtract from p hat, and we're subtracting our z star times our standard error, which was p hat q hat over n. And on this side, we're adding our z star times our standard error, which is p hat q hat over n. All right, let's make some room. So what was p hat again? Beautiful, 0.225 minus z star was, very good, 1.96. And then times our standard error for the point estimate was 0.0467. That's got to be less than p, which is less than p hat, which is our 0.225, plus c star, which was 1.96, times 0.0467. And then let's get our calculator back out and do our thing. So we will have, I'll show you a couple ways to do that, but if you're constructing it by hand, we would have 0.225 was p hat, and then minus z star was 1.96 times, and then I think we had 0.0467. Let me double check that. Yes. And we hit enter, and that gives us our lower bound, right? So we'll round that to 4 digits. 0.1335. 0.1335. And then doing it the other way, here's a trick on the calculator. If you hit second entry, it lets you edit what you did last time. So I'm going to go ahead and just change that minus symbol to a plus and hit enter, and we get 0.3165. 0.3165. Cool so far? So, what did we find out? I mean, we gotta have some sort of conclusion, don't we? Well, what we found out here was that come on, help me out. If we put this back into percentages, we could say something along the lines of we estimate with actually at the 95% level that between 13.35% and 31.65% of Mira Costa College students vape. Cool, cool? All right, let me show you another way to find a confidence interval using the calculator. All right, so again, if you go to second distribution, no, sorry. If you go to stats, here we go. We're looking at a 1 proportion z interval, okay? So here, x was equal to 18, n was 80, confidence level was 95, and then okay, so we had found this under the test. And if you zoom in, I know it's teeny right now, but it gives you the lower and upper in your p hat right there. Cool, cool? Okay. So now we're done. So that was our conclusion over here. And now let's get into sample size. So suppose we want to collect data to estimate some population parameter. How do we know how many sample units must be obtained? If we consider E to be the desired error, so basically E would be the width of the confidence interval, right? And so I'll put CI there. Then what we do is we solve the equation E. So remember that, what did we do? We added something to p hat and we subtracted something from p hat. If we hadn't have done that, we would have just had p hat. So the width comes from when we took this z star business times the standard error for the point estimate. So if we solve this for n, it'll give us the first formula below. So this formula, of course, requires p hat. If we don't know p hat, we replace p hat by 0.5 and replace q hat by 1 minus p hat, which would be 0.5, and get the estimate. So let me just show you really quick how you'd solve that. So looking at the first one, E is equal to Z star times the square root of p hat q hat over n. So here, if we were to square both sides, right, we would end up with E squared is equal to Z star squared, and then times p hat times q hat over n. Because remember, if you square a square root, then you just get what was inside the radical, the radicand. So now I want to isolate n. So if I go ahead and if I multiply both sides by n over e squared, then I'll isolate the n. And we'll have n, the sample size, is equal to, let's see, we've got two things squared, so let's just write it as Z star over E, the quantity squared, times p hat q hat. Groovy? So that's why it works, all right? And so when an estimate p hat is known, that's the formula you'll get. You'll get n is equal to Z star over E, the quantity squared, times p hat q hat. But if not, they're both 0.5. So when you go 0.5 times 0.5, you end up getting 0.25, right? And then times Z star over E, the quantity squared. Groovy? All right, so suppose, hey, maybe you're doing a statistics lab project. And you want to find out the percentage of MiraCosta College students who have used their smartphones to make an online purchase. A recent survey indicated that 51% of all adults have made an online purchase with their cell phones. Recognize that one? You guys gave that to me. All right, so a recent survey indicated 51% of all adults have made an online purchase with their cell phones. How many students should you survey if you want to be 90% confident that the sample percentage is in error by no more than 2 percentage points? All right, so we have a p hat. Do you guys see that? P hat would equal to, is there some known proportion there? Beautiful, 51%, right? Which is 0.51. Whoa, sorry. So this here is p hat. Groovy? All right, so now continuing, that would make q hat equal to 1 minus p hat, which will be 0.49. Beautiful. All right, so what else do we need to know? Well, we don't know n. That's our big question mark, right? But we do have this confidence level, right? But remember, there's two tails in a confidence interval. So basically, we want to cut that in half, right? And have this be a total of 5% of area, right? Because then, of course, you know, your other one will be another 5%, and then you'll have your region. But this will give us the z value we need. So the probability that some z1 is less than z, well, if we're barring it there at 5%, do you see that would be 1 minus 0.5 0.05, which is 0.95. So then you go to your calculator or your chart or whatever, and we go to second distribution, inverse normal, and we're looking for 0.95. And we get a value of 1.64. 1.64. So Z1 is 1.64. All right, so now we have Z star. Okay, what else do we need? Well, I think we have pretty much what we need, right? It's going to be, when no estimate p hat is known for that one. So it's going to be the first one, right? So n will equal to Z star over E, the quantity squared, times P hat times Q hat, all right? So n will be 1.64 over, 2 percentage points. That was our E, right? So E would be 0.02. And then P hat is 0.51 and Q hat was 0.49. And let's see what we get. We get 1680.3. 1680.3. But you don't want to have 3/10 of a person, right? So this one, we got an approximate of, what was that? 1680.3. But you always want to round up to the nearest human, right? So your conclusion is, I would need to survey 1,681 students. To be 90% confident that the sample percentage has no more than 2 percentage points, or is no more than 2%. All right, so that's your conclusion, and we're good to go. All right, have a great afternoon, evening, morning, whenever you're watching this, and I'll be talking to you soon. If you like the video, please subscribe.